Hello everyone, welcome to the technical paper presentation on Minecraft, automated mining of software bug fixes with precise code context. We are Sai Krishna Avula, Venkatesh Bobilisetti, Shavik Mondal from Software Engineering and Testing Lab at IIT Gandhinagar, Gujarat, India. The challenge we took up is automating precise data collection for code snippets with bugs, fixes, location, and types. Generally, any auto bug detection and fix models requires a good data set to train on. The problem with the existing datasets like Fix.js, which is introduced in MSR 2022 and Tufano et al. At TOSCM 2019, they are subjected to only single language, that is JavaScript and Java. Also, the granularity of current repository mined bug fixing datasets is usually at the functional level without any precise bug location and bug types. The major issue that has not been explored yet is bug fix context. So we came up with a solution named as Minecraft, which is nothing but automated mining of software fixes with precise code context, which got accepted at ASE 2023 Industrial Challenge Track. So we created a language agnostic algorithm where the bug fix pairs are extracted from different languages, that is C, C++, Python, and Java. And when it comes to granularity, it is way better than the existing data sets where we look at file, functions, and the statement ranges as well. And when it comes to context, Minecraft talks about the context around the bug within and outside the function. As all of us know that a model requires a huge and a proper data set to get trained. The existing data sets are just bug fix pairs with no precise location and context and are small in terms of only few GBs. But Minecraft has a whole sum of around 28.8 GB with 3.29 million bug fix pairs. And also we have attributes of precise location, bug type, and commit messages. Now, how we have attempted to solve this problem is presented in the following slides. So how is the data acquisition done? The flowchart here represents the sequence in which the dataset is created, where the first step includes project selections. We implemented a rigorous and stringent set of filtering criteria to select the projects. The first criteria is we chose GitHub projects which are real world with a popularity of more than 1,000 stars, written primarily in Python, C, C++. The first criteria returned around 923 projects with a commit count of 4.85 million. Second criteria is we took those projects whose commit count is greater than the median of total commit count, and the projects are narrowed down to 462. The third criteria is we chose projects with less than 25,000 commits and further narrowed down the count to 420. This selection provides a robust and representative sample suitable for research and analysis tasks. Now, let's look at the example workflow. To demonstrate with the example, we chose a project named Geocoder, which is written in Python. Geocoder is a library in Python, which is about geocoding services. If we look at the git diff of buggy and fixed code, we can see that there is a change in line number 25. The Minecraft maker or the algorithm has extracted the buggy code and fixed code snippets successfully with the proper context, location, and bug type. And when you look at the context, we not only included the whole function, but also included the code surrounding the function, which typically is needed if there is a code change within the function definitions or written statements for better interpretation. And if the bug is present outside the function, we provided a context of file length above and below the bug. The next step in the flow after project selection is finding bug fix commits and buggy files. The collection of bug fixing commits involved multiple steps. The commit messages were analyzed to identify bug fix commits, leveraging keywords related to bug fixes. A total of around 52 keywords are used to find the bug fixing commits, whereas the existing datasets use only 6 keywords. These are the sets of keywords we use to find the bug fixing commits. In addition to those keywords, a regular expression has been used to perform precise searches for bug fix commit patterns. So this is the regular expression we used to find the bug fix commits. Once we got the fixed commits, we use the SZZ algorithm to trace back and identify the buggy files associated with these commits. So what SZZ does, it takes the bug fix commits as input and returns bug inducing commits as well as buggy files as the output. The next step in the flow is to extract buggy and fixed code snippets. The extraction of buggy and fixed code snippets is done using location of buggy line and fixed line using tree-setter library. But how did we obtain the location? It is obtained by using the result of getDiff between the fixed and fixed minus one commit of the buggy file. The getDiff has a sequence of additions and deletions. We chose those pairs where there is an addition immediately after deletion because a fix is modification, which typically involves addition after immediate deletion. The reason for diff between fixed and fixed minus one commit and not fixed and bug inducing commit is that if a bug is fixed in the ith commit, then it's obviously present in the I minus one commit, which helps in analyzing only few line changes rather than multiple changes if the commits are far apart. The last step is to find the bug type. We used a large language model in order to predict the bug type. The LLM used is a commit message generator available on Hugging Face by Mimexit. It takes getDiff of fixed minus one and fixed commit as input and generates the summary, which is nothing but a description of bug fix and can be considered as a bug type but are project specific. The schema of our data set is as follows. We have 5 columns. The first column is before bug fix, which is nothing but a buggy code along with the context. The second one is a after bug fix, which is nothing but a fixed code along with the context. The third is the location, which represents the line numbers of buggy and fixed code. The fourth is a bug type, which is inferred from the LLM using getDiff. Fifth is a commit messages, which is obtained using PyDriller to extract the commit messages from the GitHub. Now let's talk about the downstream usage. The dataset can be used across multiple fields. For example, researchers and academics can utilize the data set for empirical studies, data-driven bug detection, autofix algorithms, and pattern mining-based bug fix algorithms. Software developers can leverage the dataset for enhancing their code quality and bug fixing process. Educators and students can incorporate the dataset into their software engineering courses or research projects. This dataset can be further improved. Suppose if we consider a bug type, we can develop a more generalized bug type classification system that transcends project-specific distinctions. Also, if we consider false positives, we can use a static or dynamic analysis to identify and eliminate these false positives and use a study. Since generally these types of data sets require a validation, so this can be either done by a manual or a semi-automatic inspection. The dataset is available at the following URL, or you can also follow the QR. Thank you.